Hmm. Um, Sorry for being a bit late. But it should be fine because today's talk is gonna be a short one. So last time we have talked about the data in alignment, and we have covered the different aspects regarding what are some good human annotation data methods, regarding how would we validate the data set, and now since we have wrapped up the data part. Starting from today's talk, we're going to talk about the training part. And specifically, we're going to talk about the post-training for alignment. And for today, I said it's going to be short because the LM prompting and the supervised fine-tuning is a kind of, many of us are very familiar with this. So we can quickly just go through the key points or key dimensions of these two topics, and then we would focus more on the RLHF, reinforcement learning with human feedback and DPO related, more complicated algorithms next time. So we're gonna take a little bit longer time next in our next lecture, which is after the holiday. I hope you enjoy the wonderful holiday in the following week. So let's start. Go ahead. Okay. As a quick recap, last time we talked about what drives human preference, where we said the human preference is driven by not only substance, such as the quality of the data regarding the accuracy, factuality, etc., but also the style of the data is very important as well regarding how we represent it and present the data to our audience. So both substance and the style are important in the data and the human preference feedback. Specifically, we talked about the different types of the human preference regarding the explicit human feedback, implicit human feedback, and some LM-driven synthetic data or LM-simulated data human feedback. And for today's talk, we're gonna talk about the LM training process, not only regarding the overview, we're also gonna talk about the pre-training, prompt techniques, and supervised fine-tuning. Are all of us familiar with these terminologies, or these terminologies are kind of new for you? Are these new for you? Yeah, good. So we would cover both using the very plain text or the languages, so all of us could understand what these terminologies mean. So no worry. And by joining today's class, you would learn the typical ways of prompting, the typical process of the LM training, and also learn the typical ways of supervised fine-tuning. And let's start with the LM training process overview and pre-training. So we know that if we want to train an LM, especially current ChatGPT one, there are several stages. They are not just like end-to-end pipeline. They actually be divided into usually like three stages where we talked about the pre-training. Pre-training is usually from the very large scale of the data trained on the big models, and then taking a super longer time to do this pre-training. After we have done this pre-training for the large model, we then do the fine-tuning. Fine-tuning also includes two types of fine-tuning. The first one is supervised fine-tuning, which is similar to pre-training, but using a much smaller data set with very high quality. And the RLHF, which is reinforcement learning with human feedback, using different algorithms, or some latest one named the DPO, direct preference optimization. They are another type of fine-tuning specifically to change or improve the safety or some of the ethical related properties of the large model. So these are the typical stages. More specifically, this is a better workflow that we can understand. We have seen these figures multiple times in our class, where it was from the ChatGPT's paper, which is Instruct GPT's paper. So they have 3 steps, and the first step are usually considered as the supervised fine-tuning, and the second and the third stages are usually considered as the reinforcement learning with human feedback. And before these, they actually also did the pre-training to make the whole process of the model. And after they have trained the LM, they would be further used for downstream applications, either directly used using in-context learning or zero-shot, or they could also further be fine-tuned to the specific applications, such as some healthcare, safety, and like etc. So these are typically the stages of training an LM. And before we jump into the most common like prompting and supervised fine-tuning topic, which might be used in our future research a lot, we might also want to get familiar with what is pre-training means here. What the pre-training is usually taken or conducted by the big companies such as OpenAI, like Anthropic. They commonly did this pre-training so that the model, when they release the model or some open like Llama, Q1, those models, they're already after the pre-training. Pre-training is usually taking a much longer time, a lot of like computational expense, etc. So that's why it is usually done by the companies. So pre-training is to train a model to understand the language, such as the words and grammar, through processing massive unsupervised text from open text corpus, such as the web crawl or Wikipedia. So here, two keywords: massive, like the data is usually very large, data size is usually very large, and unsupervised means that they actually usually don't have human annotation. They just directly scraped from the online corpus or some existing data set or online books, and they do this like pre-training one. So you can see this is the figure and the link that could provide more details about pre-training if you are interested. And there are usually 2 ways of pre-training, if you might be interested. The first, like 2 ways basically means like usually 2 algorithms or 2 methods. The first one is next token prediction, and the second one is masked language model. And these 2 methods are usually used for different model architecture as well. So the next token prediction is important that you might want to know, because this is usually the method of pre-training our GPT-based model or encoder decoder or only decoder-based model that is used for generation. And so for next token predictions, it usually uses the preceding sequence of the word to predict the next word. So typical models includes the GPT, the Llama, the Q1, and they are all only decoder in the only transformers decoder architecture. We have mentioned a little bit in our first lecture. And the FLAN-T5 is another type of model architecture, including both encoder and decoder. But all of these models are very good at generation. So you can see that this is the typical task that in the next token prediction. Basically, the model would see the tokens before, all the context before, such as Hannah is a blah. And then the model would need to predict what is the next token. And then it can be a sister, a friend, a marketer, a comedian, and these are like the task for models to do the next token prediction task. And the text, you might be interested in, oh, what are these texts from? They could be just directly from Wikipedia or from book, from, like all the online corpus, so that you give the model the previous like context, ask the model to predict the exactly token, and you have the ground truth of the original model. You compare with them using like different metrics. That is the important like method for pre-training the GPT-based model. Another type of method for pre-training is named mask language modeling. It is also important and is super popular before LM was out, like basically before 2022. It is usually used for BERT-based model, like BERT or Roberta. So these two types of model are only encoder architecture, so that they are commonly used and not for generation, but in the architecture would give the input having an embedding of the specific context and use those for classification. So the tasks are usually classification or similar tasks. So for a mask language model, you can see randomly mask some words in the sentence and use the context words on the left and the right together to predict the mask words. So for the task in the mask language models, the model would see the black one. For example, if the model would see Jacob, the model would also see reading, and then you ask the model to predict what is actually here as a verb. So it can be fears, it can be loves, it can be enjoys, etc. So this is the task for masked language model. And yeah, these are two typical methods for pre-training. And the first one is more important if you need to learn GPT-based model. And yeah, here is some, if we focus on the next token prediction task that are used for generation, which is currently we are all familiar with the LMs, there are typically two transformer architectures are used for these tasks. The first one is decoder only LM, so that it is also like sometimes named autoregressive language models. And these models include like GPT, OPT and Llama are both from Meta, and the Palm from Google, GPT from OpenAI, etc. And the encoder-decoder model is you have both an encoder and a decoder doing the generation, including the BART, the FLANT5, which is not that popular, but yeah, they are still like a typical methods here. So you can see this is the decoder-based language models architecture. This is you need to use those unlabeled textual corpus, such as from Wikipedia, and sample the data to pre-train the model. And their loss function is like this. It's the sum of log likelihood of the conditioned probability of the ith token, because it's next token generation, given the preceding k tokens over the full text corpus. So any questions here? Maybe I can finish the last one. So you can see that for this case, we actually don't need human labels here because the context itself is ground truth. Because they only predict the next token. As long as we have a full context, we would have each token as the ground truth. So that's why when we train this kind of model, the data can be scraped. We have a massive of the data resources from Reddit, from the Wikipedia, Stack Exchange for coding, GitHub for coding, etc. And Hugging Face also is also hosting the like a lot of data sets that might be used for this pre-training. But pre-training data sets can be any like valuable resources online. And until here, any questions for pre-training and the overview? Great. Yeah. Then let's come to our section part, the second part of prompt techniques. We should all prompting, like used the prompt before. As long as you have ever interact with ChatGPT, you must have ever used the prompting before. And so we can see, maybe we can have a quick like Q&A. What are the typical ways you ask the LM to do things? So for example, some people might directly ask, oh, help me draft a story or thing. Or some people might give like, I would provide with you several examples and follow this to do some like things. And what are you think is a little bit special experience that you ask the LM, the input you have ever asked the LM to do? Like, would you like to share some of the unique case? Or here we can also see maybe you are developing some unique prompting techniques. Any of you? Like prompting techniques or prompting method you have ever used to ask ChatGPT to do things?
I think one of the techniques is to give the GPT some examples, which we call the crucial learning. So basically, for example, if you want to ask the LM, like what is 5 plus 5, you can give him some example like 6 plus 6 or 3 plus 3, something like that. And this will actually strengthen the LM's output.
Yes. Yeah. Yeah. That's very great. That's like a very typical way of few shot learning, a very professional like answer as well. So it is definitely a very helpful prompting technique. We would also cover later. Yeah, good one.
This role play conference, like, oh, like you have to role play as a doctor, become having headaches.
That's also very, very good one. Yeah, it's more and more popular, I think, like nowadays to do role play so that you ask the LM to play as a specific role and then like so that they would simulate these specific roles in the world and respond to the specific answers that we want. Role play is not a very good strategy for the technique. Yes. More. Cool. Then I will show you more techniques so that it can expand your knowledge now. This is a paper that are very comprehensive. If you want to know a very comprehensive like overview of prompt technologies, feel free to check this one. This is a good paper. And it's systematically surveyed the prompt engineering techniques. Many of our today's cover is also from like this paper as well. So basically they have covered over 40 like different prompting techniques that has been ever used or mentioned in prior research and ranked the count of these prompting techniques descendingly. So you can see that the most popular one is few shot learning, as like our classmates have also mentioned, and the zero shot reasoning is another like very popular one mentioned a lot. And let's see, and I believe there's also like a role play somewhere in these like all these list here, and there are more actually, such as like good in context like examples. In context learning is another one, and prompt order sensitivity, self-consistency, etc. So you can see there are actually very like a lot of different prompting techniques than we can imagine. But like our classmates just come up like with 2 examples. So I felt like it might be helpful for you to expand a little bit more knowledge so that these techniques can potentially help you improve the performance as well of the LM. So let's see, here are 3 typical methods of prompting techniques covered in this paper, which is also like very typical in our nowadays as well. The first one is zero shot. Zero shot means that shot means that how many examples. So zero shot means no example there. Directly ask them to answer your question. And few shot means that you give the LM several or few examples so that you kind of teach LM some examples and ask them to answer you. And the thought generation, one of the typical method of thought generation is chain of thought. Do you know chain of thoughts? Have you ever heard the chain of thoughts before? Yeah, that's great. Yeah, it's a very good one for reasoning, and it significantly improved the performance of the LM as well. So chain of thoughts is a very good and effective prompting technique. And exampling ensembling basically means that they might prompting multiple times and assembled the older generations to get a better results. And a typical method includes self-consistency, which is actually the same team, proposed by the same team of chain of thoughts. So that this is one typical method, but note that all of these, like the black examples, are just one example. There are much more technologies under this category. And the other one is self-criticism. Basically means that you ask the LLM to criticize him or itself, and then it can, like, by self-reflection, it can improve like their own performance. And one of the typical techniques is named chain of verification. And the sixth one is named decomposition. Decomposition, as like it said, it's kind of decompose the complex task into step-by-step or smaller modules so that the LM could have a better capability on resolving the smaller task and then assembled to a bigger one. So this is one typical one is proposed by a group like from Princeton and the Google DeepMind named Tree of Thoughts. So these are 6 typical categories, with actually I believe there are over 40 like these smaller techniques, but we just highlighted some of typical one here. So we would briefly cover each of them so that you can get a better sense of what does all these techniques mean. The first one is named zero shot. So zero shot basically means that you just give the LM nothing. But of course, you can specify the LM to direct into some specific styles or specific roles, like we have the role-playing prompting, which is also belonging here. And the emotion prompting also means that you ask the LM to be emotional in some specific emotional status. And this paper you can check out named Bounding the Capabilities of LM in Open Text Generation with Prompt Constraints. Basically, they're exploring how to prompting the LM with the specific style prompting so that the LM could generate the specific styles that we want. And here are the 2 examples in this paper that actually failed the things they want. So for example, a human or the user is asking the LM, so write a passage about love with a humorous tone. And the style here, it wants the LM is like a love story with a humorous tone. But the LM is saying something like very objective and very cold. So that's why it's a failed case here. And the structure also, the structural one, the human one, the LM to write a sentence with 10 words about running, but the LM also just like wrote a very short one. So these are all the cases of failing examples, meaning that the LM at that time, this was like several years ago, at that time was not that very good as style prompting. And etc. You can also see many examples of role prompting, emotion, but nowadays their performance might be pretty good compared at that time. And the second case is about the few shot prompting design. Few shot is nowadays like a very common one, prevalence one. And if you are conducting research, you might need to compare with different methods of addressing something. Few shot, zero shot, chain of thoughts, these 3 methods are something you must try as your baseline. So that are some very basic like methods you need to conquer. And here are 6 main design decisions when crafting few shot prompts. Such as like the exemplars quantity, saying how many, the few, like K-shot, how many examples you want to show to the LM, only 1 or 2 or 5. So this is some like design decisions you need to make. The second one is about the order, and it shows that a different order can actually influence the performance. So the ordering of the example is another important design choice you need to make. The third one is about exemplars label distribution, saying if your task is about like positive and negative, saying sentiment classification, and then will you all show them just positive example, or you show them like evenly, one pass, one neg, one pass, one neg, or like the distribution of the data is another thing you need to decide. And the other thing is label quality. The label's quality will be very important to decide the performance of how well the LM is generating the label. And the first one is format, saying, are you using like a specific like method format to indicating the label? Are you just set them together, or using some specific like symbols to indicate the label? Those are another design choice. And the similarities, how diverse you want your examples showing to the LM. And these are some design choices. And in our next lecture, we would also show you some interactive systems that could actually help you find the best few-shot learning or the better few-shot learning that could help improve the LM's performance. But you might want to keep in mind that when you design a task to prompt LM to finish some like specific task you want to see, and then here are some design choices you need to keep in mind and you can play with to figure out the best way. And the third one is about thought generation. And one of the most common method is named chain of thoughts. And here you can see that in the standard way, let's say we just talked about the few-shot learning and zero-shot learning. And this is the typical previous method that's just use a standard prompting, ask the model to say, Roger has 5 tennis balls, he buys 2 more cans of tennis balls, and each can have 3 tennis balls. How many tennis balls does he have now? So this is kind of a reasoning task that we want LM to address. And usually here is actually a one-shot example. The user shows like just one example to the LM and then directly ask the question to ask the LM to respond. And the one-shot example, you can see that the answer is not that good. So how can we improve? Here, they actually ask the LM to think step by step. This is the philosophy of chain of thoughts. So ask the LM to think step by step of the reasoning process. And if necessarily, you can even intervene on their reasoning process to correct or to drive so that LM could now having much better results by thinking step by step, so that the LM said, oh, the cafeteria had 23 apples originally, and then they used 20, and then they had like 3, they bought 6 more, and now they have 9. So you can see this is a typical example of chain of thoughts, which had been like proved very effectively back in the 2023. And this paper was published in 2022. And this is thought generation. There are actually more. I would highly encourage you to like read more techniques there if you might need them in the future. Might need the prompting in the future. And then the fourth one is named ensembling. Ensembling, as we said, is just like having multiple of the LMs generation and then do some aggregation in the most effective way. And one of the very popular or very like high cited paper is named self-consistency, which was right after the chain of thoughts. You can see they are the same like group from the Google Brain. And this was published a little bit later in the iClear 2023. The idea is something like this. The upper one is about the chain of thoughts we just discussed. You have the prompt, you prompt the language model so that the model would using a greedy decoding way to generate the token step by step and also think step by step of the reasoning task so that nowadays they know the answer is 14. For self-consistency, it's basically the idea means that, oh, it's greedy decoding and it's one answer, and the performance sometimes is not that good. And is it possible that we can have multiple answers for the same model, and then see, and not in a like deterministic temperature setting, but using a more diverse like generations, and see, do a majority vote on their generations, and then to see what would be the best answer. And it has turned to be like much better. The performance is better. So you can see that this is the example they ask. Still several like K-shot learning fit into the LM, and then they ask the LM to answer like the how much does Janet make every day, and then basically we can ask the language model to generate multiple answers, and some answer said, oh, it's 18, some said it's 26, some said it's 18. And then after having multiple generations, they do a majority vote and marginalize out reasoning paths to aggregate the final answer. Here we can see that the answer is directly is aggregated after the majority vote as $18. So here is a good way of checking whether the model is self-consistent. And if not, they are always self-consistent, then we do an aggregation strategy as majority vote to pick the best one. So this is the idea of self-consistency. And the fifth one is named the self-criticism model, the prompting techniques. And one of the, as the name said, like self-criticism is that you ask the LM to self-reflect and self-improvement. And one of the good prompting techniques is named chain of verification, COV. And the idea here, you can see that the chain of verification method is giving a user's query, and a large model generates a baseline response that may contain like inaccuracies. And then we show a query here, like you can see here is like name some politicians who were born in New York. And then the baseline response is something, here are some politicians who were born in like New York. And then you can basically ask the LM to, again, to do some verification, and you can plan this verification, such as, okay, where is Hillary Clinton born, where's Donald Trump born, and etc. And then execute the verification, basically double check the results in a different angle. And then by combining the different ways of verification, you can get to the final verified responses. So you can see original response, we usually like the previous method are just focusing maybe on the original one, and you actually just add this intermediate one of self-verification. Plan the verification methods first, and then execute the verification to get the generation, and finally you get a verified final response. So this is one method of chain of verification. The last one is named decomposition. Decomposition, as it is said, just decompose a very complicated task into an effective way. And this this is like a tree of thoughts paper, which is also very important in the domain, that was like be used in many like reasoning tasks or complicated tasks to address those problems. And in this tree of thoughts, we can see the key ideas here that before tree of thoughts, we use like the input output prompting, such as like just 1-0 shot prompting. Or we can use like chain of thoughts, so that you ask the LM to think step by step, so that you have multiple steps here. Or you have self-consistency, where we have just described. You basically prompt LM to reason from different paths to address the same problem, so that you can see they have different reasoning paths. This tree of thoughts is more like you have multiple paths to the same output, but you find out the best or most effective way in this tree path, so that this is like the semantic of the tree, the schematic illustration of the tree of thoughts method. So it basically illustrates various approaches to problem solving with LM, and each of these rectangle boxes means a thought. So that's why it's a tree of thoughts, which is a coherent language sequence that serves as an intermediate step towards the problem seeing. So this is the philosophy of the tree of thoughts. Do you have any questions here? Different prompting. Yeah. Which one would you like to use? Yeah. So that's regarding which one would you usually to use if we are just daily use with chat with LM to do some easy task, not for research, not for just either for fun or for some like easy task. You can basically like do those type of like a zero shot or few shot, which is most common and easy. Sometimes you might need a complicated thing, saying that you ask the LM to write a paper for me or write a like address or resolve like the some game or some like play with chess, etc. Then you can maybe decompose the task into some like small processes and using some variation of, for example, decomposition way or etc. Or if you are addressing the LMs, asking the LM to address some reasoning task, a chain of thoughts is a very effective way. These are just like a daily interaction. If in the future you need to do research on the LM-based prompting, you usually need to propose your own method and have some baselines. So zero shot, few shot, and the chain of thoughts, remember, it's some baselines you have to like cover in that. And then you might propose your own method and the specific domain's best method. So these are some of how to choose and like it's not sure which one is the best, so it would be depending on your empirical study as well. Great. And no questions, right? Awesome. And now we can talk a little bit more about our third part, which is supervised fine-tuning. Supervised fine-tuning is a bit different from the prompting techniques in the way that for prompting, we just need a fixed model, and it can be directly from OpenAI, or it can be directly from some like companies, or it can be some models we trained via research, so that we don't need to touch on the model's parameter or weights or change the model in any way. But supervised fine-tuning, as you see, the tuning or fine-tuning basically means that the model's parameter or weights need to be changed after based more aligned with what we want. So that is the difference here. And so first of all, what is fine-tuning, or what's the typical process of fine-tuning, supervised fine-tuning? Supervised here firstly means that they have some ground truth to supervise the model. So basically, we either as a human annotators or either as like most of the time, it's a human annotators are actually generating some labels that are acting as the supervisor of the model, so that you are supervising the LM. So with supervised fine-tuning, it means that the data you are feeding to the model usually have human annotations. So that is why we named supervised. And with that said, the process usually, first of all, need us to curate a data set of high quality LM outputs. Examples of the LM behave correctly. So compared with pre-training, the supervised fine-tuning usually need a much smaller data set, but with much higher quality. That's why we need a human in loop to annotate these data. So then the data will directly fine-tune the model over these examples, and the models learns to replicate the style of these examples during the fine-tuning. So this is pretty much the basic process for supervised fine-tuning. Any question? Great. Here are some examples of examples. Like here, this is like one figure of the examples that we usually used for supervised fine-tuning, where you can see that here is the prompt and here is the response. And you can see this is like a much more high quality data. Specifically, asking the LM or supervising the LM to address the problem, saying, write a poem to help me remember the first 10 elements on the periodic table, giving each element its own line. And here is the poem LM, or actually human originally wrote, and then feed into LM. And this is another task you want LM to address. And this is the human annotated response you have. So this is named the supervised annotation, basically providing these helpful examples for LM to further learn. And then what is the difference between supervised fine-tuning and the pre-training we just mentioned? Since we said, oh, it's all giving some data, it's all doing next generation prediction, and it's all training. It's all changed the model parameter. So what's the difference between supervised fine-tuning and the pre-training? The key, there's actually honestly no much difference regarding the training process, but they are both using next token prediction method to train the model, but the main difference are actually in the data part, where inside of the pre-training, if you remember, the pre-training is an unsupervised way, basically means that you don't need a human there. You just need a massive corpus or a lot of data online from Wikipedia or from book, from any digital resources, so that you don't need human, you don't need supervision, and so a massive corpus of raw text data to train the model in pre-training. But for supervised fine-tuning, they actually, or most of the case, need very high quality instructions. And usually it's a one pair, like prompt to response, and this high quality pair of the data to train the model. So the data is the key difference between pre-training and the supervised fine-tuning for the model. Here are some empirical results published. This is also still from the ChatGPT paper, instructed GPT paper, where you can see that they have some different comparisons between the pre-trained model, the supervised model, and even the reinforcement learning with human feedback model using the PPO. And then you can see the green and the blue, the cyan and these bluish lines are actually means the pre-train. And the green one is actually means the supervised fine-tuning. And you can see that supervised fine-tuning could improve the win rate a lot compared with this pre-trained model. Similarly, here is also the green color means the supervised fine-tuning. And you can see that the green color is usually a little bit higher than that. And the yellow and red one is further reinforcement learning algorithms. And we will cover the reinforcement learning algorithms in our next lecture. Similarly, you can see these are another or more examples in empirical results indicating the effectiveness of supervised fine-tuning. And then we might want to discuss about the pros and cons of supervised fine-tuning. First of all, there are a lot of pros, of course. That's why we want to adopt the supervised fine-tuning. So the advantages of supervised fine-tuning includes high effective at the performing alignment and especially relative to the pre-training, it's computational cheap as well. So as we mentioned, the pre-training usually needs massive data and a lot of computing. So that is usually often the case that's very expensive. But supervised fine-tuning commonly need a much smaller data set, and it might need some human annotation, which is expensive, but compared with pre-training, it's much cheaper. And the second one is a highly effective technique for improving the LM's quality. So this is, of course, the advantages of the supervised fine-tuning. Then my question is, what's the disadvantage of supervised fine-tuning? What's the risks? Can you think of?
I guess if you want a good amount of examples, it takes a lot of human work to create the examples that you give to the model, and so that could take a lot of time and money.
Yeah, pretty good. Yeah. So that is the key disadvantage of the supervised fine tuning. You need a lot of human annotations. It's like much longer, expensive, and especially the quality of the human annotated like data need to be like very high quality, and it's sometimes very hard to guarantee that. So that's a great point. The cons of the supervised fine tuning is that curation of a high quality data set is usually very difficult. And also careful manual inspection of the data, which is usually not scalable and also is usually expensive, exactly like you said. Great. So those are some of the like disadvantage of supervised fine tuning. Could we address or avoid this disadvantage such as scalability and the expensive? So that's why this paper was like a blast, or like it's very important and prevalent since it was published back in 2022, where it's named and it's basically proposed in instruction tuning or instruction self-instruct, like later on we would cover. Basically it's like it changed or improved the current like prompting method in a way that it can be more generalizable, it can be much cheaper, and then like significantly improve the performance as well. So we can dive a little bit more here in this instruction. So what they have is that first of all, they define the task with the specific context that we want the LM to address. And then they provide several positive examples together with some negative examples. And they not only provide the output, sometimes also provide the explanations, so that you can see you don't need a lot of like these examples, maybe 5 to 10 is good enough. So which is like pretty doable or feasible for human to annotate. And then in the end, you put these task instruction into the LM and like appended for K, like multiple these instructions. And then the LM could like generate the specific outcome, sometimes even with the explanation. So now you can see this method, which is also named instruction tuning. You can also see some, if you are doing research, some of the model are released as instruct blah blah, like the same model actually have different version. Some version is named instruct, some version is like just raw name, where it basically means, oh, they might be tuned in an instruction way. So the good thing of this method, why it is so important, is that if we only consider supervised fine-tuning, the data there is like usually saying, here is one specific task, and we give them several examples of the data set. So it's specific for that task, not that generalizable. And then the model being fine-tuned might only be aligned or adjusted to the specific task that we have the human annotation. So generalizability is a big thing. But with instructor tuning, you are not tuning the LM to address a specific thing. You are tuning the LM to follow the instruction. So basically means that if the new task is here, the human only needs to give a very clear instruction regardless of what task it is, so that it basically makes these much more generalizable for LM to address much more generalizable tasks. This is the big advantage of this instructor tuning. So any questions here? Good. And here is a typical way of general pipeline of instructor tuning, where you can see that we have, first of all, the step basically divided into 2 steps. The first one is about instructor data set construction. And the second step is instructor tuning. And the first step, we can see we only need the text label as a template to have the instruction output. And then we also have some seed instruction with ChatGPT generate more instruction and outcome. And then we have all these outcome together to fit into LM and then to supervise fine-tuning the LM. So this is pretty much similar to the supervised fine-tuning, but they are actually using a different data format way to make the LM more generalizable. So to make a model a better generalist that can understand and respond to a wide variety of explicit instructions, improving its ability to follow commands and generalize to new tasks. That is the big advantage of the instruction tuning. And furthermore, based on instructor tuning, why we said like this is a good solution for address the disadvantage we just mentioned, because the same author, same group also like proposed a self-instruct. Basically, they can automate it. It's an automated framework of generating the data. So we can dive a little bit deeper here, where you can see that they have these different like examples with the instruction, with the input and the output. They give several one, and then they can actually ask the LM to generate more, so that this data is sometimes like the LM simulated, where LM generated instruction examples can like significantly expand the data set that we need for instructor tuning. And here is the process of this self-instruct method. They first of all have like 175 seed tasks with only one instruction and one instance per task, so that you don't need to annotate a lot like our traditional supervised fine-tuning. And then you give this to the task pool to ask another LM to generate more, so that you can see the step one is instruction generation. You ask this LM to follow this specific seed task and instructions to generate a bunch of like more data, instruction data. And then you use these generated instruction data feed into the LM to classify task identification. So the motivation here is that usually the instruction is not always high quality, but for fine-tuning, we need a very high quality instances or examples to train the model. So basically here, you need to do some filtering or need to do some like quality check. And here they did is like the classification task identification, and to check whether it's good or not. And here, if yes, it made output first, feedback into the task, and then if it's no, it's put the input first back into the task, so that they can do further this filtering and only select the good instructions back into the task pool, so that you can we can accumulate a bunch of great instructions to improve this model. And that is a high-level overview of the instruct, which could start from a small seed set of the task as a task pool, and then gradually use the resulting instructions and accumulate more data samples to the repository of the task. And the resulting task can be used for instruction tuning of a large model later to follow the instruction better. So this is the typical way of our instruction. Great. This is pretty much today's content. It won't have a very, very long content. So the key takeaway I think you would want to know is like knowing basically about what is prompting, what is supervised fine-tuning. We actually, most of us have ever used or know it somewhere, but today's give you a better clarification of the definition. And then it might be or somehow get familiar with the different prompting techniques as well, so that next time when you interact with the LM or ChatGPT again, you know that you actually have at least 6 different types of interaction mode to make the best or better use the LM for your own tasks. Yeah, and that's it. So today our course could finish a little bit earlier, and wish you enjoy the wonderful holiday. Thank you.